Hi, welcome to this video, and today I would like to do again a sample calculation about catalyst particles in the famous Haber-Bosch reaction, and therefore we of course first look at the given task which we want to solve or talk about, and then we use the Ergun equation to solve this task because it's of flow through a bed of particles, and then we change the pellet size, so the size of the particles. We decrease them, and then we take a look what changes for the pressure drop in our system. So imagine you're a young process engineer at a fertilizer company, maybe you know one or two, a famous German one maybe. The company operates a Haber-Bosch reactor where nitrogen and hydrogen gases react over a packed bed of iron catalyst pellets. So we have iron particles and we have nitrogen and hydrogen gas, and they react due to the catalyst particle. And the management is considering replacing the current catalyst particles or pellets with smaller ones to boost the surface area. So to increase the surface area, to accelerate the reaction, the idea is use smaller particles, and your job as a engineer is to check whether this change would cause a very high pressure drop, which cause more costs because you need more compression power across the reactor, and your job is basically to check if it's worth to do or not. So the pellets at the moment are 3 millimeters. The porosity of the bed is 0.45, so 45%. The density of the catalyst particles, the iron, is 6.5 kilogram per cubic meter. The viscosity of the gas stream is 2 times 10 to the power minus 5. And the superficial gas velocity is 0.2 meter per second. So it's a quite decent gas flow. So large particles and small gas flow. And the task here is that you calculate the pressure drop per meter of the bed with the current pellets. So calculate the pressure drop for the system, and then you take a look at the different fractions. So we have a friction term and we have a pressure term, and the question is which of these dominates, and could we also use the Karman-Kutzeni equation instead of using the Ergun equation. And in the last task you should check if we now replace the 3 millimeter by smaller pellets, 1.5 millimeter, what happens to the pressure gradient, and is this trade-off worth or not. So can we use the smaller particles, right? Okay, so first let's take a look again at the Ergun equation. The Ergun equation basically describes the pressure drop per length, so per meter, and this is also what we need in the task. We calculate per meter, and then we have two parts. We have this term and we have this term, and this is a friction term and this is a pressure term. So this is the friction of the fluid with the particle, and then we have a pressure difference within the or around the particle, and this is described by the second term. And the friction depends linearly on the fluid velocity, on the viscosity, and the pressure depends squared on the velocity and on the density. And then we have here the porosity of the bed, the influence of the particle, and some numbers. So we can directly start with B, because A is to calculate this and B is to calculate this, and it's easier to calculate first friction and pressure and then overall. So Ergun equation consists of two terms. We first investigate the pressure drop based on the viscous fraction. That's the first term in the equation. So this is 150, 1 minus porosity squared, viscosity of the system, velocity, and then we have here porosity cube and particle size squared. So if you put in all the numbers, it's quite straightforward. We have all the numbers, don't forget the velocity, and you will end up with a pressure drop of 0.22 kilopascal per meter, which is a very low number, but we have quite large particles and a very low or slow gas flow, right? Okay, then now let's take a look at the second part. The second part in the Ergun equation is the pressure term, and for the pressure term we have this equation, this term, this part from the Ergun equation, 1.75, density of the fluid, 1 minus porosity divided porosity cube, particle size and velocity squared. And if you again put in all the numbers, we have all of the numbers. Be careful with cube and here is not squared and here is squared and so on, and then we will get a number of 0.92 kilopascal. So now we can put both together to get the total pressure drop. So this is the friction term plus the pressure term, and this is 1.14 kilopascal per meter. So if we now consider the task, this is a very low pressure drop. So this pressure drop is basically negligible because in the reactor we have 150, 200, 250 bar and even more. And if you consider a bed which is not 1 meter but around 10 meter, this pressure drop would be still less than 0.1% of the pressure drop. So this is completely negligible. That's good news for us, so we don't have to waste a lot of energy or money due to the pressure drop. And if you also think about the question, could we use the Karman-Kutzeny equation? No, because the dominant term is the pressure term, and the Karman-Kutzeny equation is just the Ergun equation without the pressure term. So it's the friction term, so using the Karman-Kutzeny would underestimate the pressure drop. Even if the pressure drop is negligible, the result would be completely wrong compared to Ergun. So now we can take a look what happens if we decrease the particle size, because if we now halve the particle size, we again first calculate the friction part, right? So this is the term of the friction. If you put in all the numbers, you just have to change this size here, and now we end up with 0.89 kilopascal per meter for the friction term, and for the pressure term we have all the numbers in here, and we change again this 1.5, 10 to the power minus 3, and then we have 1.84 kilopascal per meter. So if we put all together, the pressure drop per meter is 2.73 kilopascal. So this is still negligible because it's still very low, so we easily can decrease the particle size to 1.5 millimeter. Now you could maybe say, okay, but why do we do this calculation? Always the pressure drop is negligible. No. So because if we would decrease the particle size further, this would increase quite fast, and also 0.2 is a very low velocity. And if you, for example, would increase the velocity, we have linear here, we have squared here, and we can say, okay, what would be under this condition, 1.5 millimeter, the maximum velocity? It's a very good task you could do. And if we say that we allow maximum 2% of the system pressure as pressure drop, so not more than 2% is allowed, then we easily would reach this maximum if we go to 0.9 meter per second. So the pressure drop increases very, very fast with decreasing particle size or with increasing velocity. So even if you think, okay, this is negligible, less than 0.1%, it explodes extremely fast. Okay, but under the conditions here, we can easily work with these pellets. So I hope you got the task was clear for you. And again, this was a task to train the Ergun equation, play around with the Ergun equation and get an understanding of how pellet size influences the pressure drop, and also we discussed shortly how the velocity would influence the pressure drop. With this, I thank you for watching the video, and I hope it helps you a little bit to understand pressure drop calculation. Thanks.